Like I got everything started now. So many things to learn about how to do this streaming stuff right. Lots of buttons over on my OBS. I got everything started now. Oh. So there we go. All right. So yeah, on my OBS, that's what I use. So for those of you who are curious. I still have probably way more things to learn about that, but we'll figure it out. All right, so I finished up grading the assignments. Actually, I just finished them up about an hour ago or so, and they look pretty good for the most part. The only thing, there's a few misconceptions. I want to go over some of those misconceptions. All right, so I think one of the most common mistakes I saw was on number 1, which asked you to compare a KB versus a KB. No. I'm sorry, that's not what it did. Little k, big B. So this one is 10 to the power 3 bytes. And this one is 2 to the power 10 bytes. This one is 1,000. This one is 1024. There were at least a couple people who answered this question. KB versus KB. And indeed, this is 10 to the power of 3 bits. And this one, both capitals, is 2. Sorry. Oh, no. This shouldn't be 10 to the 3rd. This should be 2 to the 10th. 2 to the 10th bits. And this one is 2 to the 10th bytes. And in this case, there are 8 bits equals 1 byte. So, there's just a miscommunication, I think, or a misunderstanding of the capitalization and where that matters, right? Because the reality is this and this are not the same. And that's an easy mistake to make. I can understand how people would make that mistake. All right. So, a couple other things. So one of the assignments that I went through, where is it here? I know I have this open. Oh yes, here we go. All right, so is this site Platinum Data Recovery Hard Drive Capacity? And so what this does, it actually gives you a smaller capacity. Well, what happens if we want that? 49 terabytes. Oh, that's interesting. And why is this? That's an interesting question. hard drive not have all the memory? Probably should use storage. Why don't hard drives get the full capacity? On Quora. By the way, this is one of my favorite sites. I like going on Quora. It still has this fair amount of trolls, but it's not a bad site. All right. The trolls tend to get ignored better here, and that's nice. So it's more about answers to questions. All right. So if you're referring to, say, showing that much in Windows, it's because of how the size is measured. To be sold as a 500 gigabyte drive, it must be at least that many bytes of storage. Storage vendors use the metric style of 1,000 bytes equal to a kilobyte. This is caused probably because 1 kilobyte was actually 1,024 bytes. To account for this misnomer, that many bytes was classified as 1 kibibyte. Ah, yes. Mebibyte, and so on. As for how your storage is shown, Windows use it. So this would tend to actually make it bigger. This doesn't answer the question completely. Ever has full capacity shown as box. This is because there is a part of the storage reserved for cache and other stuff that the storage service needs to work, like drivers. Right. This probably isn't true. I think it's a lot closer than 32 to 28. But that's a good example of that. And it's a good place to get questions to all kinds of different things. All kinds of different things. So if I want to buy 100 terabytes just because, I've got extra money just laying around. I don't even know how much a 100 terabyte hard drive is. That's a lot, though, I think. Yeah, it would be. All right, so that's a little bit there. I just thought this website was really interesting. So, okay. So on number 4, IBM. One of the big things. Oops. So I didn't really talk about it in great depth, but what happened was IBM had been failing to get a PC put together, and then Apple beat them to the market, and they were pretty upset about this because they've been failing, not being able to get it to the market. So what they did was they gave like a last-ditch effort to a team of programmers and told them you have a year to get it done. Well, the problem is in that year they couldn't have done everything that they needed to do. They just aren't Steve Wozniak. By the way, that's the guy who programmed the Apple and most of the Apple II. Great character. Really, really neat guy. But anyways, they needed to do it quickly. So what they did is instead of developing everything in-house, which is what Apple still does to this day, you can't buy an Apple hard drive from Walmart. It's not possible. I don't think you can buy it from Walmart. You can only buy it from Apple certified stores. You guys all know that. Well, this is the reason why is on regular PCs, we don't even call them anything. They're on the same architecture as the IBM PCs were. And that's because they used third-party components, including the Intel chip, including some of the hard drive stuff, including some of the disk drive. I mean, there's just a ton of different things that they used third-party stuff. And then they just kind of mashed it all together, and they made it work. And it actually worked fairly well. But the big thing was it was open architecture. Probably misspelling that wrong. Close enough. Oh. There. An I. So many people put in, that's what open architecture is. That means you can put third-party things in and they will work because you've given people the ability to do that. It's actually kind of interesting because they said, well, you won't be able to figure out our chipset for our motherboard, and so it won't matter that you don't know. Well, when they did that, within like 36 hours or something silly like that, somebody had already cracked it. It was uncrackable. That's what IBM said. It was so complex. So a lot of people put open source. And open source is something different. So we can't put open source onto a piece of hardware, which a computer is. The operating system that runs on it is the software. So open architecture says this is how the pins are situated and all those kinds of things. So where, how many different wires are actually in the specific cable, and those things are all part of the open architecture. And how they actually work, like there's a lot of different specs that we could go through, and we're not going to do that today, but there are things out there you can figure out. Open source says that you have a computer program, you create a piece of software, and the source code is available to you. That's what open source means. Now, sometimes that means that the thing is free. It's only kind of free. You can't do whatever you want with it, and you can't use it as a basis for something you're going to sell, but otherwise it doesn't cost any money. But you do have to agree that you're not going to use it for commercial use. So, or at least not directly. In any case, but open source could be that, right? You get your brand new game on your Xbox, and they send you the source code as well. So that would be possible. That does not happen for any game that I know of. For the most part, there are some open source games out there that are actually kind of interesting, but open source says that you get the computer code that was used to generate that program. So that's important. Okay. So also, IBM's original price, $2,000 to $4,000. If I had $4,000 for a desktop computer, I could make an awful nice computer. I think for $2,000 I could make an awful nice computer. It's just interesting. And that was, what, in the 1980s. So that was back when, I don't know, I suppose we could look and see what the cost of different things were. That's an interesting thing to do. But that was most of the things I had to talk about there. Okay, so we're going to come back and we're going to do some more talking about K-maps. Oh, yes. Assignment 3 has been posted, and it is due on Friday. And I'll work on getting assignment 2 corrected as quickly as I can here. And then we'll continue moving on with that cadence. Let me bring up the schedule. Oh, I thought I had it open. I don't. Okay. So here's our schedule. This is the week of the 12th, right? Okay, so this represents the Monday that we're looking at. So we're going to look at 3.4. We already started and did a lot of the stuff in 3.4, but we'll do some more on it. And maybe we'll go back and do a little bit of review on 3.3 or 3.2. And then I'll finish out the rest of the chapter, most of the rest of the chapter this week. And then next week we'll do the same thing, and then the following week there will be the exam. So just plan for that. Looks like that'll be due on the +4 on that, the 30th. I could just look at my calendar. Yeah, the 30th. So just be aware, and that one will be a little bit different as far as being able to turn it in late. Because I don't think I'll take late. I won't take anything late on that exam, so it'll have to be in by 5. So plan accordingly. Have 2 to 3 hours to work on it. Ideally, I'd like to see you get it done in an hour, but my guess is some of you will take longer than that, and that'll be okay. All right, so all right, let's go back to K-maps. So I said that I was going to talk about don't care conditions. Don't care conditions. Hey, I should have put my phone on silent. It's in the other room ringing. But now it's done. So, okay. Hopefully it wasn't my mother. Okay, so don't care conditions. So, sometimes we're modeling something that doesn't take all of the bits. And the book uses an example that I think is a good one to talk about digits, right? If it's going to do 0 to 9, right? Those are our digits in decimal. And we want to represent those in binary. Instead of using like an ASCII code, we want to actually just talk about the value of those, right? And so 0 to 9. And we don't care about the rest of the numbers in the base 2, right? Because there's more to it than just those 9, right? We have to go up to 16 because in order to capture that, we would have to get all of them. So that's what we talk about in a K-map for don't care conditions. So it's not possible, right? We can't get anything higher than a 9, and so we can't get the values. So let's just look at the table here, and we'll actually, we're going to call them X, Y, and Z are the 3 bits, and we'll just do it straight in order. So we'll say 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Oh, I suppose I need a W, don't I? Because it's 4 bits. Oh, that's a bummer. 2, 4, 6, 7, 8. And then what I'm going to do is I'm going to put some lines in here the other way so that it'll help us keep it straight. And do them every 4. All right, go back to this. 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1. 1, 2, 3, 4. 1, 2, 3, 4. Oops. Zero, 0, 1, 1, and 0, 1, 0, 1. And I'm not going to do the rest of them, and part of the reason why I'm not going to do the rest of them is because we don't need to worry about them, because they don't exist. Because that's 12 of them, and we only have 10. So So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh. No, I'm going to do the rest now that I think about it. 0, 0, 1, 1, 0, 1, 0, 1. And so, oh yeah, this would be 10, but 10 doesn't exist. So what do we put here? Well, in this case, what we're going to do is we're going to put an X there. Because I don't care. These are things that can never happen. I'm just going to put big X's. So over here, if I look at a formula, so f is a function, some function here, and I'm just going to pick some values for this K-map. Let's go 1, 0, 1, 0, 1, 1, 0, 0, 1, 1. That'll give us 6 ones, and then the rest of these are X's. And we're going to use those X's when we create the K-map. Alright, so let's go up here and create our K-map. So this side will be WX. So we'll have 0, 0, 0, 1, 1, 0, and 1, 1. And then up here, we'll have YZ. Again, 0, 0, same 4. Nothing special here. Alright, so 0, 0, that's these two. Let's just look at these. So that'll be this category here. Actually, it looks like I made those lines in the right places to help me here. So the 0, 0 here, that's going to be a 1. So let's put a 1 there. And then the 0, 1, that becomes a 0. And then the 1, 0, that's a 1. And then a 1, 1, that's a 0. So then we go down to the next grouping, and we say that's a 1, that's a 1, this is a 0, this is a 0. And we go down here, and we see a 1, 1, and then we're just going to put X's in the rest of those spots, because there I don't care. Which means they can be either 1s or 0s, depending on what we decide we need. Alright, so now in a K-map, one of the things I didn't talk about before, but it does apply, is that we can wrap from one side to the other. So if I wanted to go from here to there, I could do that, right? So if that was a 1, I could create this group of 2 here that spans, like this. Right? But that's not a 1, so I'm not going to do that. So I'm looking for groups of 1s. So I could do this one. This is a rectangle. That's 4. That's a nice little one. That's nice. But I see a bigger one because, oops, because the X's can be in. So since the X's can be in, let's do this one. Very nice. Okay, and then this one here. So I could either cut off here at the end, or the bigger the group, the easier the map is. So it's better to do this, generally speaking. So this one, this is a perfect example where we can match, because we can go bottom to top, or top to bottom like this. So that'll be that one. And then we just have this one left. We could just circle that one, but we can also put it into a box like that. Okay, so let's start looking at these. So this one here says the y and the z are 0 and 0, and then the w and the x, they change. They both are in all positions. So we can just say, since it has to be in this position, y naught and z naught plus. So if there's a group of 1, then all variables must be in it. If there's a group of 2, lose one variable. A group of, it's not 3, it's 4, isn't it? Is the next one. 4, we lose 2 variables. Group of 8, we lose 3 variables. Okay, so we've only done this one, so let's do this one right here next. So this one's a little tougher. What doesn't change? Well, both the w and the x are changing. They're flip-flopping on each other, but that's okay. They're not changing. And here, the y is not changing. Oh, we should be able to lose 2 variables, and we're not going to be able to. Okay, since the y is always no good, we can say y not. And the z could be either one, so we can throw that one out. Now, we can't throw out that the w can be either one because it's not consistent. So here we have to say, y naught x w x naught. Continue it on the bottom line. So let's look at, so that's 1, 2, so let's look at this one, 3. Here, that turned out it wasn't better than just doing a smaller one. Right? Let's just try doing this one instead. So just like with a lot of things in this class, not everything, but a lot of things, there's more than one way to do it correctly. Right? Because we get to decide how we do these. We say, this one's hard, so this one's a little harder, so let's go ahead and switch gears and not do it that way. All right, so in this case, these are the only ones we really needed because we just needed to pick up that single number. In this case, y stays the same at y naught. And both w, that stays that, and that is that. So we don't need to do this side of it because that's going to get caught up when we do this bottom one here. Well, let's do that one now. Okay, so let's look here. W stays the same. It's always on. And X flip-flops back on and off. And Y and Z could be any values that you want. So that's it, just W. So if you have a W that's on, that makes this whole statement true. because these are ORs, right? So this is an OR. So the other ones, all these other groupings could all be false. We're going to have one more here, but it could all be false, and this one's true. So if we look over here, all of these from this dashed line down, we'll never see them. They cannot happen. So we look here and we say, well, all the time this W is 1, then this is 1. So that's correct then. So anytime we see a W on, we don't have to look at anything else. It's kind of handy. All right, well, let's look at this one here. W changes. X changes. Y and Z both stay the same. Wait. No, they don't. Oh, yeah, they do. What am I talking about? Okay. So W changes. X changes. So I know I need a Y and a Z naught. I should have to do one more. Oh, actually, the value W and X. I could have done the same thing here. This is W exclusive or X. Oh, the right, which would have been like this. That's exclusive or. It's a plus sign with a circle around it. All right. All right, so this gives us our K-map and a sum of variables. Aha, okay. So let's grab this. All right, first off, I want to grab this and pull it over a little bit. Well, that didn't exactly work. No, move the whole thing like that. There you go. Okay, go like this, then go like that. Evidently, I didn't get this Y. Oh, or this. Okay. There we go. Grab this, throw it on the end. Okay. Now, we get everything? Nope. All right, try it again. Copy that. Go down here. Paste it in. Okay. So, because we want to have it for reference here. Oh, yeah, that's right, our purple line. There we go. Okay. So let's create a grouping of logic gates from this. All right, so we have, well, we're going to have a negative. All right, so let's start with W. W coming in. And we know we're going to have to go ahead and branch that off. So let's put the dot there to branch it off. Now we have a not W. And let's do the X. Does that have a not in there? It never does. Okay, perfect. All right, so then that we just go ahead and leave that alone. And then we have a Y. And we need both versions of the y. And then the z. And we only need the knotted version because it only appears twice in both places. It's a complement. Okay, so let's do the first one. Why not? Oh, there we go. And they're going to end together. All right, that gives us our first one. So now why not W naught and X? Put those three in together. Then we just have W, and that one just goes ahead and pull that one through. So now let's do this one. This one's a little bit trickier because we have to do this first, don't we? But wait a second. That's weird. No, I did this wrong. This has to be, it's, oh, that's an interesting, okay, so it's X, they have to be the same, so we're saying that they have to be the same, which means, no, there isn't one for that. There's not one that we know of. Oh, it's a NOR gate. An exclusive NOR gate. Go back over here. Why am I not scrolling anymore? It's just lagging on me. Interesting. All right. This is wrong. This is exclusive NOR. Because we need these to be the same. So W exclusive NOR. I'm just going to write it like this. Oh, geez. Oh, there we go. Aha! We have a website for this. Exclusive NOR. Recall, this is a NOR gate, right? But we put equals 1 in here, And then we put that's it. The rest of it's all in NOR gate. So we put the equal 1. The reverse or complement of the exclusive OR. So it's the negation of it. So, a NOR gate doesn't have that little dot on it, does it? Okay. And then if we look, right, so we could say OR, exclusive OR, not. Oh, okay. And here's our truth table. Both on, yep. Both on, yep. One of them on, but not the other. Nope. So, oh, that's interesting. So it has to be 2 out of the 3. Or 3 out of the 3. Oh, wait, no, all on doesn't work. That's interesting. Maybe we could go through that some other time. Right now, I'm not going to do that. But exclusive OR. So that actually is X not. There we go. And we could have used XOR for this box right here. This one would have said Y exclusive, W exclusive OR. So we could have done it like this. Need that there. So that would have been equivalently the same. So I could have done the bigger box, and that wouldn't have knocked out a variable, but it does change the dynamics of it. Okay. But we're not using that one, so we don't have to worry about it. Okay. So which ones have we done so far? We did this one, and this one, and this one. Oh, that's the only one we have left. Okay. All right, so we need a Y. First, let's do our exclusive OR. So we need a W. Okay, that's good. We need the W. Let's do that. And an X. Put that in an AND. No, not in an AND. Into an OR. An exclusive OR, though. And then we put the little thing in here. This gives us our exclusive OR. Our exclusive NOR, I'm sorry. XNOR. Not to be confused with other things that sound similar. Okay, so then we bring this up here, this Y, and then the Z naught. So and then we just AND those together. So then we bring this and this. There should be one more. Oh, W, which I terminated and then try to get them close together. Just make a big gate. There's our function F. So you can think of this similar to electrical current in some ways. Well, not like electrical current. I mean, ultimately that's what it turns into. But we can kind of think of it that way. So what we do is we say, well, let's turn this one on. So this one's positive. It's glowing, right? That one's... Well, let me take a copy of this so I can kind of destroy it. I don't want to destroy this. This beautiful thing that I've made. Let's copy that. Come on down here and paste it in. Oh, no, bring it over here. There you go. Let's put that there. All right, here's our one that we're use. Oops, cyan. There we go. All right, so let's look at this one. So let's assume we get a W Y signal. Just WY. Okay, so that makes this one hot. What it means is that the X or the Z is not hot, or it's cold, so then it becomes hot once it goes through there. So this is on. This is a positive value. And we get a positive value there. And one positive value coming into here. Okay, so this was positive, so that makes this negative, so we're not going to change that one. This is negative, it doesn't go through any knots here, so then this one is positive, so this one's on. Oh, we've got two. And this one's off. Okay, so let's evaluate these. We've gotten all of them that come in and got them to at least to their first gate. So let's look at this gate here. All of them are off. All right, let me use blue here. Blue for off, or no current. So this comes off. Actually, this should be red coming off there till it gets to the NOT gate. Goes through the NOT gate and it becomes blue. And then it splits down here. That's also blue. Okay. And this should be blue coming into the NOT gate. And this is blue here. Blue going into there. And then blue going up into here. Okay. So we look at all three of these. They're all off. They have no current. This requires all three of them to be on. So this is a simple one. We know that this one is off. Oh, I wrote the wrong gate at the end here, didn't I? This should be an OR gate. Man, that looks really sloppy. But that's why I'm a computer science teacher, not an art teacher. Okay. All right, so let's look at some of the rest of these here. Let's look at this one. This one's easy, right? They're one's on, one's off. If this was an exclusive or exclusive and, that would be okay, but in this case it's not. So we know this one is. Just go ahead and be dead. Okay, so then we go here, and this says, right, remember it was exclusive, so that means they both have to be true. So only one has to be true, if one of, because we do the exclusive OR part, and then we negate it. So it's an exclusive OR, so that's true, and then we negate that before we kick it out, so we get a blue coming out here. So we had two reds and a blue, but all three of them have to be the same in order for it to come out of an AND gate. So let's go ahead and do this up to here. So now we've got all four of them. We've got three blues and one red. But indeed, what's the reality here is this was going to be red because this is an OR gate and just one of them carries the day. And we could go back and look and do this again for some of the other ones as well. But just a way to kind of visualize that, how the true and the falses would flow through this. All right, well, let me look here to see. I think that was all I really have. What I could do is, what I'm going to do, actually, I think this is a good idea. Oops, I don't want that one. I want the other version. There we go. Okay. So here's, this is all fine and good, but don't need to talk about it, except for this. Construct an XOR operator using only AND, OR, and NOT gates. Shouldn't be too hard. So let's do the NAND gate. Let's make a NAND gate. No, yellow. Come on now. Shouldn't take too long, then we can be done. All right, so let's make a NAND gate. So first off, let's remember what a NAND gate is. It says not and. So it's the opposite of an AND gate. Oh, actually, NAND is really super simple, but that's okay. So this will be a 1 here. Or no, in an situation, this would be a 1. But since it's the opposite of NAND, it's a negation of NAND. So let me back this up and conceptualize this a little differently. We can say X and Y. So we go 0, 0, 0, 1. And then here, it's the complement of that. So we get 1, 1, 1, 0. All right, let's build a gate, or a group of gates for this. Well, it looks to me like, since it's the opposite of AND, let's just do this. Let's do an AND. And then a NOT. That's it. So if you think about this, let's prove this out. Let's go ahead and go X is positive and Y is negative. Okay, we're going to give, so first we need to label these, I suppose, X and Y. So this one's positive, this one's negative. This whole thing, right? It's an AND gate, so it requires both to be red or both to be positive. So we'll go ahead and make that blue there. And then if a blue comes in, then a red goes out. If a red comes in, then a blue comes out on that gate. So this is turned on. So that means that for this value, X, Y naught, that is true. So let's look over here. X is on, right there. Y is off, right there. Look at that. Perfect. And what's the answer here? The answer is, yep, it's on. And indeed, actually, it is on. And we could test the other different ones here to go through there just to double check it. But I'm going to assure you that they are correct. I'll leave it to you to do that checking. All right, let's try doing another one. Well, I don't want to do an exclusive NOR. That's pretty interesting. Well, what other special ones do we have? So far, we have the and the or. No, that's why, because I have to flip back farther. The and, the or, the not. Oh, the book shows the not differently, doesn't it? It shows it, yeah. There's different ways to do it. The book shows it like this. Where's my mouse? Come on, mouse. Shows it like this. That's a not. I don't like this way of doing them. I like this way of doing it so it's obvious. So it doesn't look like an and. Oh, yeah. Okay. Ah, and then nor and not. Then exclusive or. Well, let's at least do the. Well, do I need to? I don't know. All right, let's try doing something here. Let's do one that's not named. Let's do this one. Oh, that's a NOR gate, isn't it? Let's do that one. That one's a pain. That'll be good. Okay. Now, the only thing we can do is and, or, and not. Okay, how do we represent this one? Well, we could simply do a product of sums, can't we? We could. That would make it just fine. That would work. All right. So this says x through a NOT gate and y, in this case, I'm not going to need the positive version. So this is an and. That takes care of the first one. Now let's look at the second one. Ah, that's an x and a not y. And then I put them into an OR gate. That's our F. That's it. That's all we have to do. That was a lot of gates, isn't it? 1, 2, 3, 4, 5. Yeah, it's a lot of gates. But it gets us there. Certainly gets us there. All right. Any specific questions? Let me mention that I am available for Zoom meetings during the day, but you have to set up a time ahead of me, probably at least a day before, so I can check my schedule and make sure everything's good. So, because the place I work allows me to take 15, 20 minutes to meet with a student and then just make that time up later in the day. They're very, very gracious about being, giving me time to be able to do that. So, major props to Thomson Reuters. That's my client. That's who has to okay that. So, but that means if you send me email, today or so, it's likely that I can try to fit you in tomorrow. It's possible that I can do it quicker, but don't expect that I can, because it's possible that I just either wouldn't see it because I don't have it up all of the time. And for those of you, I think I put on there. Did I put on my my Saturn Systems or RBA email? They're one and the same. They go to the same box. One company bought the other one. RBA bought Saturn Systems. So if I've put my email for that, you can use that if you want to send me emails. I probably don't respond to that. I very rarely get information there that's super relevant. So I don't monitor that as closely as I do the ARCC one or Minnesota State one. So send it to my Minnesota State box. That's probably just a better place to send it. All right, I think that's it. I know we're 20 minutes short, but unless there was any questions, it doesn't look like there's anything. So today was a little bit of review and go a little bit more in depth and do some more examples. But it's all good stuff, and we'll come back and do some more things with gates. Now, I promise you that we will do gates now on Wednesday. All right, I think that we're going to stop now. All right, bye-bye.